for the introduction. Yeah, I will talk today about the investigation of twin boundaries in cadmium zinc telluride. Quite uncommon way of characterizing these twin boundaries. But first, maybe very quickly to my person. So my name is Gradwohl, and I come from Montanuniversität Leoben, which is a university based around mining, very similar to the one here in Freiberg. It's also a very small university, so only about 4,000 students. It's not as old as the one in Freiberg, that's why I always call it the little sister of the University of Freiberg. So a quick off from my side. And yeah, maybe to the collaboration. This is a project within ÖAD project, so within the Austrian Academics Exchange Fund. And it's a collaboration between the Northwestern Polytechnical University of Xi'an, of the group of Professor Yadong Xu and PhD student Dong Qiangpeng. Yeah, first to radiation detection devices. So radiation detection devices have, of course, many applications in nowadays society, probably no military applications. And in principle, what you do is you want to have a perfect single crystalline, for instance, cadmium zinc telluride, which is a very prominent room temperature X-ray detection material, and you apply a very high voltage to this crystal, so about 5,000 volts or maybe 10 kilovolts. And whenever an X-ray photon hits the detector crystal, you generate an electron hole pair and you can detect it electrically. So this is about how such a detector unit might look like. Maybe very basic stuff to cadmium zinc telluride, you might already know. It's a 2-6 semiconductor within the cubic spheroid crystal structure. So it's a crystal structure very related to the diamond structure. Spheroid, maybe a funny anecdote related to mining, comes from the Greek word sphalerus, which means treacherous or sneaky. And what's so sneaky about the spheroid is it's a zinc sulfide mineral, so it has the density of other metal minerals, but you cannot really reduce it by carbon, so it was not possible to reduce it until the 18th century. And therefore it looked like a valuable mineral, but it was actually not valuable until the 18th century, and therefore Sphalerus. Yeah, it's within the space group F4-3. M is a direct bandgap semiconductor, and you can tune the bandgap between 1.5 and 2.2 eV, depending on the zinc content. So 2.2 eV is the bandgap of the zinc telluride, and 1.5 of the cadmium zinc telluride. And for usual X-ray detection applications, you have X of about 0.1, so that means 10% zinc atoms within the crystal structure, so 10% zinc, 90% cadmium. And this leads to a direct bandgap of about 1.6 eV. Yeah. So how do you produce these cadmium zinc telluride crystals? It's quite difficult to grow cadmium zinc telluride single crystals, and therefore you use a modified vertical bridgement method, where you in principle have a 2-segment oven. One segment is a little bit above the melting temperature of the substance, the other segment is a little bit below, and you just move very slowly through this oven, and therefore you generate a very huge grained cadmium zinc telluride. So you just make very big grains, and the idea is then you can cut out your detector crystals in between the grain boundaries and twin boundaries. So one essential step of generating these high quality detector crystals of cadmium zinc telluride, which are necessary to produce reliable X-ray detecting crystals, is to cut out the detector crystals in between this polycrystal. And here you can see this is about the ingot, how it looks like. So the growth time of such an ingot is in the order of a month. So the growth speed is really slow. And here you can see it's not a single crystal, it's a polycrystalline material. And yeah, we investigated a bicrystal sample. So you cut out a cube of about 5 by 5 by 5 millimeter of the CdTe material, and we wanted to have a twin boundary exactly going through the crystal. So I have a bicrystal with a twin boundary in between. And the reason we did that was to investigate the impact of twin boundaries onto the detector performance. And we used Kelvin probe force microscopy to investigate the sample. Kindly, today, Kelvin probe force microscopy was already explained, so I will just skip to the results, so I don't have too much time. So here is the topography image of the bicrystal. So the twin boundary goes in principle exactly here through, and on the twin boundary nucleates the tellurium inclusion. That's quite interesting, and due to the polishing process, the telluride inclusion was partly removed. And you can see here in the contact potential, this Kelvin probe force microscopy measurement, that you have here the contact potential of cadmium zinc telluride. You kind of see the twin boundary coming from here towards here, and here there is like still a little bit of tellurium left inside the inclusion. So the tellurium piece was not completely removed from the inclusion, from the pit. There is still a little bit of metal inside. And you can clearly identify that by Kelvin probe force microscopy, and you can also get more information out of how the interface between tellurium and cadmium zinc telluride works. Furthermore, related to interfaces, it turns out that the interfaces of these tellurium inclusions inside the cadmium zinc telluride twin boundary form 111 cadmium zinc telluride facets. So in principle, the cadmium zinc telluride determines the facets of the inclusion, and the tellurium just follows what the cadmium zinc telluride tells it. So you can clearly see here the crystal facets, and they are associated with certain distinct crystallographic orientations. Another big topic inside the crystals are dislocations, or the dislocation density within the detector crystals. What happens is, so the glide plane of the spheroid structure is the 111 plane, and it follows the 110 directions within the crystal. And the dislocations move until they hit the tellurium inclusion, and they start to form areas of increased dislocation density around the tellurium inclusion, which is exactly along the 111 planes of the crystal structure. So if you cut here and make the polishing plane exactly 111 CdTe orientation, then you end up with this hexagram of increased dislocation density, which is shown here by cathode photoluminescence measurements. Maybe I will talk here about the interface between the two twins. So when the two twins hit each other, they have different orientation to the polishing plane, and therefore you would expect a slight difference in the contact potential between the two halves of the crystal. And we were able to detect that with KPFM, and also see the impact of illumination on this junction between the two crystals. So the junction grows, and also the difference in contact potential gets bigger with illumination. So clearly photoconductive. And now maybe to the characterization of the twin boundary. If you measure the twin boundary with AFM, and you can clearly see a step between the two crystals. So this is crystal 1, this is crystal 2. In between is the twin boundary, and what's interesting about the twin boundary, it has steps inside. And you can in principle use these steps to characterize exactly which twinning system you have within the crystal. We used here EBSD to determine the exact orientation of the polishing plane. Of course, you get two different indices for the two different crystals because they have different orientations due to the twinning. And this is a completely coincidental orientation of the crystal. So that's why you have quite high Miller indices in this sample measurement. There goes the huge twin boundary through the whole crystal, so about 5 by 5 square millimeter. And the first suggestion would be that this is the 1-1-1 twinning system, which is the most common twinning system in the cadmium zinc telluride structure. And let's say we assume that, of course we can also prove it later. If we assume it's the 1-1-1 twin plane, which is a coherent twinning system in the cadmium zinc telluride crystal structure, then we can think about what are the steps within the twin boundary. So first suggestion would be, again, it's 1-1-1 twinning system, but it turns out that it actually cannot be a 1-1-1 twinning system, and I want to explain now why. So I already mentioned if you have a polishing plane which is oriented in the 1-1-1 direction, and you look at the number of all the 1-1-1 facets which are possible, which are the glide planes of the cadmium zinc telluride structure, and you cut it in the 1-1-1 direction, yet then you end up with this regular hexagram. But if you look at coincidental planes, like for instance the 5-1-6 and the 4-1-5, which we determined by EBSD, then you end up with some stellated hexagram. And these stellated hexagrams are now the orientations of the 1-1-1, the intersections of the 1-1-1 planes within the cadmium zinc telluride structure and the polishing plane. And if you now compare these two different stellated hexagrams, then of course there is this plane here, which is the 1-1-1 twinning system we were talking about before. But we see that no other 1-1-1 twinning plane could ever make this 90-degree angle over here. So it's completely impossible that it's a 1-1-1 twinning system, and then you can use an error minimization technique to find the Miller indices of the missing twinning system, and it turns out this is exactly the 2-1-1 twinning system, which is a semi-coherent twinning system. So you have like little gaps on every second layer of the CdZnTe structure. And yeah, this fits exactly the angles measured in this topography measurement here before, and explains how these steps within the crystal structure form. And yeah, we also needed some 3D information of how the planes are inside the crystal. So if we look with AFM from the one side, we can also look from other two sides, but we still are never sure how the twin plane goes through the whole crystal. And therefore we use infrared microscopy. And the point is, cadmium zinc telluride is pretty much transparent to infrared. So you can see through the crystal, but the tellurium is not. The tellurium is a dark spot within the crystal. And therefore, since the tellurium inclusions kind of decorate the twin boundary of the bicrystal, you can clearly see the twin boundary inside the infrared microscopy picture. And you get a 3D information of the alignment of the twin boundary relative to the crystal, and you can correlate that. And this again proves that we have the big twinning system 1-1-1, and the steps within the 1-1-1 twinning system, which are 2-1-1 twinning systems. And it also suggests that there must be a third kind of twinning system, which I didn't indicate here because it's still a matter of how stable this twin boundary is, if it's really a twin boundary or maybe just steps of different kinds of twin boundaries, or it could also be just some kind of grain boundary. Nobody really tells us if it has to be a twin boundary exactly here. But yeah, if you compare it to calculations and theoretical models, then we see the 1-1-1 twinning system, which is the most common system, is coherent, and 1-1-2 is laterally coherent at least, so only in one direction. And yeah, there are also first principles calculations on this, But to observe it experimentally, you would need a transmission electron microscopy measurement and in principle count the single atoms and compare them. But with this approach, you can in principle do macroscopically AFM measurements and use this error minimization technique to figure out the twinning system. And yeah, this is the result of the characterization, and it indicates that here we have a 1, 0, 1 plane, and since this is a very low indexed plane, it is highly likely that there is some kind of dissection of this system here. I'm not sure if it's a twinning system, I have to admit. Yeah, and we also did detector performance measurements on this bicrystal, and in principle what you do is you send a very short pulse of X-ray radiation to the crystal, and usually you have then this peak of the short pulse, and then you have like a signal decreasing here, and you get also a second peak if you have a coherent twin boundary in between. And this signal in general is much less sensitive to X-ray than the crystal without twin boundaries. And yeah, in principle, the conclusion is that the twin boundary has a detrimental effect on the detection performance. And it's important to understand how the twin boundaries form to control the detector performance of the cadmium zinc telluride crystals. Yeah, I would like to thank you for your attention. I hope you have some questions for me.
Yes. Thank you, Mr. Gradwohl. Also staying in time, so we have 2 minutes for questions, and hopefully you're in good shape to raise these questions. So everyone was overwhelmed by all the different crystal planes in there. So I've got just a quite simple question, probably not coming from the field. If I look further at the application of these crystals, it's typically in electronics, isn't it? And the size of these telluride inclusions seems for me quite large, yeah, disturbing the structure. Do they have an effect, a function, or is it just a kind of impurity?
They have definitely they have an effect. So you grow the crystals not the cadmium zinc telluride and also the cadmium telluride phase has in principle no solubility for telluride. And you grow them on purpose with not 50% cadmium, 50% telluride, but you use like 50.5% telluride. So you generate these inclusions on purpose because they are here to catch the inclusions. So we have seen here that the inclusions end up at the telluride that the dislocations end up at the telluride inclusions. So the telluride inclusions catch the dislocations, and then you cut out your detector here. So you skip the telluride inclusions and the dislocations, you throw it away, and you just use the pure crystal, which has very low dislocation density and is very homogeneous.
Okay, it's a cleaning process somehow.
In principle, yes. Yeah,
very structural cleaning,
form,
yeah.
Actually.
Yeah. Okay. So, do we have further questions? I'm sorry that's not the case, and thank you again, the speaker.